Okay. All right, so we're doing a caddis problem to warm up as usual. Happy Wednesday, everybody. Oh, there's Kenny. All right, great. Uh, this is what week the end of week 13. So we got more time, but not a lot. We'll make the best use of it, and we can. All right. So all modern banks employ information systems to process their data. The amount of data is enormous. Imagine all the transactions, payments, e-banking, web services, etc. Yeah, this is and yeah, e-banking, right? This is actually what my son does is try to provide security for banks and authenticating that a customer is a real person rather than a bot, and without things like CAPTCHA, which is one way of doing that, I guess. In any case, therefore, advanced data structures must be used to store the data and allow access to these data quickly. A binary search tree is one example of such a data structure. It holds a collection of values with some comparison operation that provides linear ordering between those values. So then this is a common abbreviation, BST, for binary search tree. Consists of nodes. Each of them contains one value that has at most two subnodes, the left and the right. It's a binary search tree. And the left subtree always contains only values strictly less than the node value. The right subtree only values greater than or equal to the node value. Okay, greater than or equal to. So you could have the same value more than once, but if it appears, if you're going to insert it into the tree, you're going to insert it to the right. As a consequence, values may easily be looked up by traversing the tree recursively. We begin with the root node. By the way, you haven't done this one, have you, Dave? Let me get the chat thing going here because I didn't have it up. All right, and we've got Kenny and Dave is here twice. Good for you. All right. I was wondering why we had an extra person, but okay, good. And all right, I'm going to get rid of that that you can't see anyway. All right. So back over here. We begin with the root node and compare its value with the value we are searching for. Depending on the result, we descend either to the left or into the right subtree, but we never need to walk through both. All right. If we want to insert values to an existing tree, then the procedure is also simple. The first value when the tree is empty is always put as the root. If the tree already exists, we start with the root node and traverse the tree recursively, as in the case of searching. Recursively, all right. When the traversal leads us to a missing subnode, we create a new leaf. Am I too far down? That's okay. We create a new leaf at that position and assign it a new value. The figures below show the tree after subsequently adding the following sequence of numbers. And they've got a picture here, which I guess, could we make something like that? What do we see? Yeah, I guess you'd have like a 3, and then a 3. Is there any way of doing this without graphics? Let's see. I suppose we could have like that, and then there's a 3 and a 4. Okay, and then 3. What? 4. This is the other slash, huh? And then 3. Oh, that's a 3. Okay. And then, I don't know, this is kind of working. I don't know. I just, yeah. And, all right. Oh, I think we want, oh, no, we don't. Okay. 4. And then the 4 will have a slash going that way and another one going that way. And then followed. So if you want to insert a 3, yeah, see, that isn't in the right place, is it? Well, no. Okay. Yeah, it is, right? So if you have the 3 and the 4 and you're going to insert another 3, then, well, 3 is greater than or equal to 3, so it goes to the right. And then you look at the 4 and you say, well, it's less than 4, so it goes to the left. All right. And do we have space for another one here? So, oh, I don't know why. Why is it doing that? What are we looking at here? So we're okay. So if we've got the 3 and the 5. There's a 3 and a 5, and we're going to insert a 4, right? So the 4 goes to the right of 3, goes to the right of 4, but it goes to the left of 5. And so we insert the 4 here, huh? And I'm just checking that that's, yeah, okay. Okay, so we have some more to do. Do we have enough room for another one over here? Okay. So here's 3, a little tedious, I know. Here goes the 4. Oh, I see. Now we're going to have a 1, I think, right? Because, yeah, we inserted that. Oh, for some reason it wants to be highlighted here. I'm not like, oh, I've got insert on, I guess. Oh, so is this, oh, and so now, yeah, so we've got a 1 here, yeah, and then the rest of this, I don't know, 4 and so on, yeah. So there's a 3 and a 5, and to the left of the 5 is that 4. Okay. Do we want to do the 2? Where's the 2 going to go? Well, it's going to go to the left of the 3 and to the right of the 1, right? But I think we get the idea at this stage, right? You may notice that different permutations of the same numbers will often result in the same binary search tree. For example, the tree from the 5th figure above. All right, that's this one, right? Oh, that's this one. Well, it's this one, right? Maybe constructed by 3 different input sequences, right? And is that right? Okay. So 3 4 3 5 4, 3 4 3 5 4, or 3 4 5, right? That would line up like that. And then you insert a 4. Well, the 4 is going to go to the right of the 4, but to the left of the 5, right? So it would go there. And then the 3 would go to the right of the 3 and to the left of the 4. And this one would also produce that same result, right? 3 4 5, and then 3 4 rather than 4 3. Interesting, isn't it? It's a rhetorical question. Your task is to compute how many different permutations there are that will result in the same binary search tree. So the input will consist of several trees, each of them specified on 2 lines. The first line will consist of an integer n between I continue to believe that's a Unicode character, but I don't know. The number of values in the tree, and the second line consists of those n values separated by spaces. Okay, so if inserted in the given order, form a binary search tree to be examined, all values will be between 0 and 1,000. The last tree is followed by a line containing a single 0. Okay, and then the output is for each tree, output the total number of different permutations that would generate the same binary search tree. As you may notice in the sample output, this number may exceed 232. Okay, so if you got 5 nodes, let's see. I need to look at the okay. So these are the different inputs, and this is the output for the first one. And I guess I'll scoot that over a notch. This one, it says 45. And really? Oh my goodness. Is that? Yeah. So that has 31 nodes. And there they are. I guess they don't quite fit. Can I put it over there? All right. And obviously that doesn't parse well for the comment section, but I think that'll work. Okay. So do we understand the problem? Well, understand all the words. So let's try to get that 45. Or first of all, let's get the 3, right? So we have what? So if the input is 5 followed by 3, 4, 3, 5, 4, then the output is 3 because there are 3 different binary search trees. Well, what binary search tree will that 3, 4, 3? Is that 3, 4? That's this one, isn't it? 3, 4, 3, 5, 4. 3, 4, 3, 5, 4. That's this one, right? So there they are. 3, 4, 3, 5, 4. And so you'll end up with this tree here, and there are 3 different inputs, a total of 3 different inputs that will lead to that. So I guess, does it have to start with 3, 4, 5? What if you were to have 3, 3? Well, then, yeah, you wouldn't have that 4 there, right? So, if it was 3, 3, then this would be a 3. So if it's going to be this binary search tree, I think you have to have 3, 4, 5. Oh, no, you could have 3, 4, 3. Yeah. So 3, 4, 3 or 3, 4, 5. And there's 2 ways of doing 3, 4, 3. If it's 3, 4, 3, then it can't be followed by a 4 because you need to put a 5 in this position here, right? If it's so you could start with 3, 4, 3 to get this part of the tree, and then it would have to be followed by a 5 and a 4. Or you could have 3, 4, 5, in which case either the 4 or the 3 could come next. All right, well, let's try to do the okay, so wait, so this is in fact what they gave us. There's 45 of those. Oh, gosh. Okay. So I don't know if we're going to be able to reason out how could there be 45 different sequences leading to the same tree. What is that tree going to be? Um, 3, 4, 5. So this is 6 nodes, and we need one more node, right? Which is followed by a 2. So let's go ahead and finish this. All right. So we got. I don't know. Can I? Maybe I can. Can I copy this here and paste it in here? Oh, yeah, that kind of almost worked. So where's the 2 going to go? Well, it's less than 3. Oh, yeah, it's going to go to the right of the 1, which means we can't quite fit it in here, right? Can I just put a 2 right there? Yeah. Well, I could separate these guys out a notch, huh? And then put the 2. Yeah, how about like that? Okay, so I'm just drawing that stupid tree. And I'm obscuring it, aren't I? Okay. There. Okay. So, how many different input sequences will lead to this same tree? Okay, does it have to start with a 3? Yes. Like this is whatever it is, it must start with a 3, because that's going to be the root node. The one on top here is called the root. And then it could be followed by a 1 or a 4, right? So essentially you're going to have 3, 1, or 3, 4, 2 different initial pairs that lead to the same tree regardless. But you can't have anything else, right? If you were to have a 3, 3 or a 3, 4, oh sorry, 3, 4 is one of them. You couldn't have a 3, 2, right? Because the 2 would then be where that 1 is. So it must be either 3, 1 or 3, 4. Okay, so if it's 3, 1, that could be followed by a 4 or a 2, right? It couldn't be followed by a 3, because then the 3 would be where the 4 is. It couldn't be followed by a 5, because then you have a 5 where the 4 is. Okay, and it has to be one of these 1, 2, 3, 4, 5 numbers to be this tree. So I see there's 2 ways to have the second number. Given the second number, if it's a 1, there's 2 ways to have the third number. If it's a 4, then what do we have? 3, 4 could be followed by a 1, or it could be followed by a 5 or a 3. 1, 3, 5. It could not be followed by a 4. Right? If we had 3, 4, 4, then the second 4 would be where the 5 is. If you have questions about this, just chime in. Okay, so so far I've got 2 possibilities for the second one. If it's the first of those, then there's 2 possibilities for the third one. If it's the second, if you start out with 3, 4, then that could be 3, 4, 1 or 3, 4, 3 or 3, 4, 5. Okay, so if it's 3, let's consider. So I'm making, I'm pencil and papering a little tree here, which is not a binary tree because now we have 3 branches. 3, 4 could be followed by either 1, 3, or 5, and still lead to the same tree. Uh-huh. It could not be followed by a 2, 3, 4, 2. Right, because then you'd have a 2 where the 1 is. All right. So I'm pencil and papering here. Well, maybe I should draw what I'm showing here. Can I do that? I'd have to go here and say, oh, it's actually on. So I just go here and say what I'm looking at. Do I have the cursor here? I don't see it. Oh, it is there. Okay, sorry. And so what I've got here is, initially it's going to be a 3 or a 3, 1. Okay, so the initial one has got to be a 3. Okay, let me get rid of that. The initial one has got to be a 3, right? That could be followed by a 1 or a 4. This 1 could be followed by a 4 or a 2. Should we put them in order like 2, 4? Oh, that's now hard to read, isn't it? There. I don't know. What am I doing? Okay. So then the 3, 4 could be followed by a 1, 3, or 5. So I'm going 1, 3, or 5. And so how many paths do we have now? We have 1, 2, 3, 4, 5 paths. Okay, so 5 ways to get the first part of that tree. And it'll be the same no matter which one, right? Oh, now I got to look back up here. Oh, can I go over here like so? And okay. So 3, 1, 4, 2, 3, 5, 4. Okay, so far I've got 3 of my, what is it, 7 values? Yeah. So I placed 3 of the 7. Oh, yeah. And so suppose it's 3, 1, 2. What could the next number be? It would have to be a 4, right? So there's only one possibility here. Oh, let's draw that this way, okay? That has to be a 4. If it's 3, 1, 4, then the next number could be either 2, 3, or 5, right? Yeah. So there's 3 possibilities here. Here's 2, 3, or 5, huh? That's a 5. I didn't leave enough space for it. Yeah, measure once and cut twice. Okay, so if it starts out with 3, 1, so far I've got 4 different ways it could go to the next 4 to get the whole first 4. Okay, so if it's 3, 4, 1, then again it could be 2, 3, 5, right? Yeah. So I don't know, can I? Yeah. 2, 3, 5. Is this working? All right, and then 3, 4, 3. Again, 3, 4, 3. You could have 1 or 5, but you couldn't have a 4, right? If it was 3, well, yeah, there are 2 4s. 3, 4, 3, 4 would lead to a 4 where the 5 should be. Where, yeah. So so 3, 4, 3. You could follow that with a 1 or a 5. And 3, 4, 5, you could follow with a 1 or a 3. All right, well, I'm kind of losing it here with this diagram. And I'm going to end up with 45 different paths, which means I'm going to have 45 leaves in the tree. Oh, hold on a second. I'll be right back. Okay, so let's start writing these out. All right. So according to my diagram here, we could have. How about I put it over here? We could have 3, 1, 2, 4 so far, right? Or 3, 1, 4, 2, or 3, 4, 1, 5, or 3, 4, 1, 2, or 3, 4, 1, 3, or 3, 4, 3, 1, or 3, 4, 3, 5, or 3, 4, 5, 1, and there are 2 5s, right? Is that right? No, there's only 1 5. So we couldn't have 3, 4. Oh, that last. Oh, 3, 4, 3. 3, 4, 3, 5, and 3, 4, 3, 1. Okay, I guess. Oh, 3, 4, 3, 1, or 3, 4, 3, 5, and then 3, 4, 5. You could follow that with a 1. You couldn't follow it with a 2, right? Because then we'd have the 2 where the 1 should be. So I didn't put this in my diagram because it was getting too crowded, right? But we could. So if we have 3, 4, 5. 3, 4, 5. You could follow that with a 1, or with a 3, or with a 4. So 3, 4, 3. Is that? Sorry, 3, 4. Yeah, 3, 4, 3, 1, or 5, and 3, 4, 5. 3, 4, 5 could be followed by a 1 or a 3 or a 4. I said that before, but it's hard to remember. 3, 4, 5, 1 can't be a 2, right? 3, 4, 5, 4 I think also works, right? Maybe I should put these the other way about, right? So 3, 4, 5 could be followed by a 1. 3, 4, 5 could be followed by a 3. 3, 4, 5 could be followed by a 4. And that's the first 4. So there, how many ways to do the first 4? I don't know. Count them, right? 58 minus 48, is that 10 or 11? This is 5. 5 more. Yeah, so we've got 11 ways to do those. How are we going to follow this up? So if we have 3, 1, 2, 4, that's this part of the tree, right? This first. So where is that? What could follow there? I suppose we could actually. So I guess I'll. Tab that over a couple times. Okay, so 3, 1, 2, 4. I'm still getting the hang of this, right? So I think if you want to get the hang of it, you just got to sort of work it through and think about what you're doing while you do it. So 3, 1, 2, 4 could be followed by either a 3 or a 5, but not a 4. So we could have a 3 here, or 3, 1, 2, whoops, 3, 1, 2, 4, 5, but not a 4. Okay. 3, 1, 2. Okay, we covered the 3, 1, 2, 4. There was only one possibility after the 3, 1, 2. So 3, 1, 4 could be followed. Well, 3, 1, 4, 2. 3, 1, 4, 2 could be followed by either a 3 or a 5, right? So 3, 3, 1, 4, 2, 5. I think okay, so 3, 4, 1, 5. So I'm looking back up here at the tree, which I'm obscuring. Maybe I'll just turn me off there. So 3, 4, 1, 5 could be followed by either a 2 or a 3, right? 2, 3, 4, 1, 5, 4, 1, 5, or a 2. Oh, we covered that, or a 3. 3, 4, 1, 5, 3 would be okay, right? That would lead to that same part of the tree. Are we going to get 45 of these things, or can we start cutting to the chase here? So what principle are we following here? And how would we represent the tree? Do we need a data structure to represent the tree? I mean, certainly there are data structures for that purpose, and that's largely the stuff of 7B. Yeah, this is kind of a tough one, huh? There weren't that many people who tackled this one. I think there's some brilliant insight that we need to have, right? So 3 cannot be followed by a 5, cannot be followed by a 3. It cannot be followed by a 2. So 3 has got to be followed by 1 or 4. But either one, right? So we see that we have a whole bunch of ways to start with 3, 1, and then even more ways to start with 3, 4. So if you start with 3, 1, have we gotten all the ways to do 3, 1? If we start with 3, 1, it's got to be either a 2 or a 4. If we start with 3, 4, then it could be a 1 or a 3 or a 5. Right? So maybe I'll. So we don't have any choice in the 3, right? All right, so the 3 has got to be the 3. The 3 could be followed by either a 1 or a 4, so then we have this bifurcation, right? If it's followed by the 1, then you could have either the 2 or the 4 next, but nothing else. If it's followed by the 4, then you could have the 1, the 3, or the 5. Yeah, okay. I started this and decided better. Is one comment. Yeah. Right. Well, we may have to come back to this because we have now exceeded our time allocation. All right. So I think we made some good progress. We understand the problem. And we could start by, oh yeah, so I should just leave it alone, right? Um, 45, huh? What is it about 45? Well, it's 3 times 3 times 5, right? So if you're multiplying, what if you're adding? Well, I think we're probably multiplying. So there's only one way to get the first thing, right? I should go back to the. I'm just thinking about this a little bit more because it's hard to let go. Only one way to get the first thing, right? So done. 2 ways to get the second thing. Yeah. Right, and there's only 2 possibilities for the second number. Notice that 45 is not divisible by 2, right? So we just, even though we have this sort of initial bifurcation, they're into one group. The 3, 1 group there's 4 of those, right? Whereas the 3, 4 group, we haven't. Oh, there may be actually more than 4, right? Because we only have 5 of the 4 numbers here. So it's 3, 1, 2, 4, 3, 3, 1, 2, 4, 3. That has to be followed by a 5 and then a 4. It can't be a 4 and a 5, right? So it's got to be 5 and then 4. So there's only one of those. 3, 1, 2, 4, 5. That could be followed by either a 3 and then a 4, or a 4 and then a 3. 3 and then a 4, or it could be a 3, 1, 2, 4, 5, 4, 3, right? All right. And if it's 3, 1, 4, 2, 3, 3, 1, 4, 2, 3, so I'm sort of placing those in my head. Then it has to be 5, 4, right? Because if it was 4, 5, that would not be the same tree. So it has to be 5, 4. So there's only, one way to finish that. 3, 1, 4, 2, 5 could be followed by either a 3 or a 4. So I could go 3, 4, or I could go 3, 1, 4, 2, 5, 4, 3. 3, 4. Okay, and I think that's all of the 3, 1, 4s, or the 3 1s, right? And how many are there? 6. 45 is not divisible by 6. 45 is 6 plus 39. So there must be 39 of these other ones, right? And what's 39? 39 is 13 times 3. Oh. So we kind of want to partition. Yeah. All right. I think we better leave this and come back to it. All right. So this turned out to be, what did he say up here? The rhetorical question. Where was it? Oh, I think it's down here. Interesting, isn't it? Oh yes, it's fascinating. Okay. So many different things to talk about. Well, we have our thread of the calculator. So let's go ahead and leave this. And I think if I say exclude, it's going to ask me to save it. And yes, I do want to save it since I had not even tried to compile anything yet. I hadn't written any code. Understand the problem is often... well, if you really understand the problem, then you understand all the different solutions, right? And that's not that level of understanding that we were looking for, but I guess we were working towards, right? Okay. What have we got? I'm going to add existing item. I think I have an ongoing calculator program, which is, I think, is PPP 6.3. Was that it? And this is 427, so I'm going to assume that's what we left off with last time. And yep, that looks like it, huh? Okay. Then in the textbook, we want to be back here in chapter 7. We want to get the variables in there, right? So let's read what he has to say about variables. And for that, we will go to our handy textbook. Okay. Having worked on style and error handling, we can return to looking for improvements in the calculator functionality. We now have a program that works quite well. How can we improve it? Well, the first wish list for the calculator included variables, and we decided to save that for later. So here it is later. Similarly, for scientific calculations, we like built-in named values such as pi and e, just as we have on scientific calculators. Yep. Adding variables and constants is a major extension to the calculator. It will touch most parts of the code. This is the kind of extension we should not embark on without good reason and sufficient time. Here we add variables and constants because it gives us a chance to look over the code again and try out more programming technique. So what would a variable look like? Well, the key to both variables and built-in constants for the calculator program to keep a name-value pair so that we can access the value given the name. We can define a variable like this, right? And we could use a built-in data structure like pair, right? I think that's one we've used before, right? And we would have a pair of string value objects, or we could have, I think you can also have a tuple, which would be, we talked about this last time, right? But let's go with his suggestion. We'll try to follow the text fairly closely. So I'm going to copy this. And where would we paste it in our code? Well, we've got the factorial, we've got our token. I mean, it's sort of a, it should come early on, right? Because it's a major building block. So how about right here at the beginning? So we defined our user-defined type, named variable with a capital V, which is a common practice to have user-defined types be capital letters. And we're going to have the variable name will be name, and it will also have a value. All right. So we're going to have a variable token. All right, let's go back to the book. We will use the name member to identify a variable and the value to get its value. Okay, so how can we store the variables so that we can search? Well, we're going to want a vector of variable objects called var_table. All right, let's go ahead and paste that in. And I guess that's a global variable, right? We do have vector, don't we? Oh yeah, standard library facilities, right? So we now have a var table, which, by the way, is very, very much like what your compiler has when it keeps track of your variables. I think there's, is it actually called var table? I don't know. Should we go to the browser and do a little searching for that? Where are we? How about here? So I'm going to search for C++ compiler variable table. Oh, I don't think it's a symbol table. Yeah, a symbol table in the compiler. Geeks for Geeks wants to tell us about it. Stack Overflow has, what is that? That's a question about it, right? Symbol table, well, let's go ahead with this first one here. I was reading Effective C++ 3rd edition, and in item 2, prefer const enums and inlines to defines. Scott Myers, yeah, he's another luminary in the world of C++. Yeah, he wrote Effective C++. Mentions the symbol table. He explains that defines may not appear in the symbol table. Based on the answer here, a bit of the suggested reading thereof. Oh, it's the thing about the internet. Everybody's always inviting you to take another path through the maze of rabbit holes. And the Wikipedia article, there's yet another path. I would define the symbol table as follows. Since the compiler only creates object files for every translation unit, object files, those are the .o files you may have noticed, right? We still need a way to reference symbols between the translation units. This is done using a table that is created for every object file so that symbols can be defined at a later stage. By the linker, when the executable library is created from the object files. Yeah, the executable or the library. During linking, symbols are substituted by their appropriate memory addresses. With their appropriate by the linker. Okay, their memory addresses. So here's what I'd like to know. Says who's this? I don't know. I guess is it down here? You get the person who's asking the question. Is my interpretation correct? After linking, once the memory addresses have been resolved, we'll get back to our variable table, but I just sort of wanted to put this on the table. Then maybe let's cut to the answer here. Symbol tables exist both for compiler, and the compiler puts even local variables in them. And then the compiler puts even local variable symbols in them. Even the preprocessor has some sort of symbol tables for the define names. So what's a define? Have we used this much? It's like a macro, I think is, yeah. I'm sort of seat of the pants extemporizing here. Um, I think if you do it hashtag define preprocessor directive, then whenever you see the following thing in your code, it just substitutes literally what the symbol is defined as in the code. Um, there's only 5 upvotes here, so maybe this is a little bit esoteric. Should we go back to the, I know one more. Symbol table is an important data structure created and maintained by the compiler in order to keep track of some of the semantics of variable. That is, it stores information about scope and binding, information about names, information about instances of various entities such as variable and function names, classes, objects, etc. Yeah. Okay, well, let's just say that when we do this with symbols, it's very much, and this whole calculator, I think part of what you want to take away from it is you're kind of building a compiler. You're building a parser, and that's what a big part of a compiler is, the parser, right? How do you make sense of a sequence of characters? And we're sort of building a compiler for mathematical expressions, and we now want to add variables into that mix. All right, so we can put as many variables as we like into the var table and search for a given name by looking for the vector elements one after another. We can write get value, and here it is. We do, we will. So here it is, get value. All right, can I just copy and paste directly from here? I suppose I can. Try to stop me. So Control C, we'll put that on the clipboard. But let's read what he has to say about it. We can write get value function that looks for a given name, string, and returns its corresponding value. Okay, let's. I just put that right here, huh? Okay, once we've declared that we have a var table, then we can pass, so we take the string. Now the var table is a global variable, right? So we have access to it at this level, right? And I know you're supposed to limit the scope of your variables and maybe later, but you can see that var table should have a wide scope, right? We want access to these variables from almost any place in the program. So it makes sense for it to have global scope. I mean, kind of like your compiler will have access to its symbol table. All right, so in any case, I'm going to save a line of code here. So return the value of the variable named s. So we pass the string s into get value, and we access by reference the variable table. Oh, yeah, right. So variable, right. So no, sorry. For every variable v in our vector of variables var table, right? So this is that range-based for loop. So we want to say for every variable v, and why is it by reference? I guess we don't want to make a local copy. I mean, it doesn't have to be by reference, right? I don't know. I suppose we could research as to the ins and outs of using a reference variable here instead of a value, a copy. But let's just leave that and say if we hit on our given string, right? So v.name, that's one of the basically variable just has two public member variables at this stage, right? And so we can access the name this way because it's public, right? And compare that with our target, And if we find it, we're going to return its value. If we don't, why is this underscored here? Expected a declaration? Oh, yeah, of course, because I have a... if we don't find it, we're going to throw an error, right? Because why would we be looking for a variable that doesn't exist? And there's our error message. I don't think that's going to work very well with the error function. There's two error functions. It's overloaded, right? Should we look those up and make sure that they're right? So I'm going to say, add existing item to what we got here, and I think somewhere in here is standard library facilities.h. Okay, so I'm going to open this up and say, look, we got an error function here that takes a single string, and we got another error function here that takes two strings and concatenates them and calls error with a concatenation. Is that what's happening with... yeah. Okay, well, that should work. I don't know. So we're just basically what this version of error does is take these two strings, concatenate them, and call error, same function, only with a single string, which is the concatenation of those two strings. Why not just concatenate them here, right? There. Not sure why he does it the way he does it. Let's see if that'll work. In any case, let's go back to reading Strustrup. The code really is quite simple, he says. Go through every variable in var table, starting with the first and continue to the last, and see if its name matches the target string. If that's the case, return the value. Similarly, we can find set value. All right, and here it is, set value, to give a variable a new value. Okay, so we just put that right in. Let's see, sorry, it was 58% were accepted for 2 points. Yeah, that was noting on the that calculator problem. I don't forget Scott's hair. That's a reference to... Oh yeah, the hair! I knew there was something. Yeah, there's a joke about... Oh, okay. So since Jonathan has brought this up, we're going to have to... all right. Well, let's see. So I put this on the clipboard. Let me go ahead and paste it in here. Scott Meyer... Oh. So this is supposed to be set value here. Oh, I want to put it up here. Get value followed by set value. And so here we're going to be reading in a string, and same range-based for loop for every variable v in our var table. If it's already there, then set its value. What if it's not there? Oh, well, then we'll need some way of adding it to the table, right? And that's going to be an issue, right? We only want one definition for each variable. But yeah, so what's the best way of getting a quick shot at? Let's go to the, Okay. So Scott Meyer, C++. What was the other phrase? Ski Man? Oh, He-Man. Sorry, right. Oh, image search? Okay. Okay. So, yeah, so this is the joke about Scott Meyer. That he looks like Print Valiant, or Yeah, yeah. So yeah, I remember watching that. Yeah, he had some good points about that. Uh, and so, what was wrong with dragging it to the trash can? Oh, yeah, 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 yeah. Huh. Yeah. In any case, hey, so here's his book, right? And it's published by O'Reilly. That's a fairly well established computer science venue. Uh, but yeah, so if you're looking for things to do over the summer with your, you can go to well, let's see, Scott Meyer, uh, CPP Con, and yeah, CPP Con. So there's a bunch of these talks available. Oh, am I in images still? All right. Whatever. So let's get back to the matter at hand. Um, okay. Yeah. Um, in any case, where are we? Um, let's get back to there, and I guess we'll back to our text. All right. So we can now read and write variables represented by the user-defined type variable, and we have a vector of those in our var table. How do we get a new variable into the var table? So we need a way of defining a variable. What does a user of our calculator have to write to define a new variable and later get its value? We could consider the C++ notation, right? And this is no um, coincidence that it's sort of the same thing, right? When you're declaring a variable in C++, it's very similar to what we're going to be doing in our calculator, right? We're going to be saying, yeah, I've got a new variable. What type is it? Well, I guess all our variables are doubles at this stage, right? We don't really have a type system with our variables. Although that'd be something to consider too, right? Uh, we were able to sort of overload the modulus operator to handle doubles. So that kind of worked. Anyway, uh, but all variables in this calculator hold double values, so saying double would be redundant. Doubly redundant, you might say. Could we make do with simply var equals 7.2? Possibly, but then we would be unable to tell the difference between the declaration of a new variable and a spelling mistake. Um, what? So if we got this statement here, so we're introducing a variable var1 equals 7.2. We're defining a new variable called var1, and this is going to be declaring a new variable called var2. Why? Uh, Clearly we want var2 equals 3.2, but we didn't say so except in the comment. We could live with this, but we'll follow the tradition in languages such as C++ to distinguish declarations with initializations from assignments. Right? So this is very much like in C++. When you introduce a new variable, you have to declare it, and we declare it by what type it is. But we're going to use the keyword let. All right, and so let is going to become a token that says introduce a variable to the var table, and it had better be one that's not already there. That'll be another issue to deal with, right? So yeah, this is sort of the very mathematical, right? Let x equal, and then give a very detailed description of what the variable is. That's when you're using the algebraic method to solve a problem. the first step in the algebraic method is to introduce variable or variables needed to solve your problem, and you should define them clearly. So if you say let x equal the car, that's a typical mistake a beginning algebra student will make, because they're thinking in their mind, oh, the speed of the car, but it could also be the distance the car is driven, right? So what about the car? That's not going to be a big issue for us here because we're just going to have a variable name, but it's also sort of biblical, let there be variable. Okay, so the grammar would be, so we've got a calculation. A calculation could be a statement. What happened to expressions? Well, a statement, there's two kinds of statements now, right? There's a declaration statement and there's an expression statement, right? And then we have these other sort of print and quit. And then we have a calculation statement. So calculation. A statement could be a calculation. Oh, sorry, a declaration, right? A declaration or expression. So we could have yeah. So let the declaration is going to be something that has this keyword let. So that says, oh, here comes a declaration of a new variable. We need to know what's the name of that variable, and we need to know what its value is. And we can assign the value either with a simple number, a floating point literal, or we can define it with an expression like 2 plus 2. That would work, right? So calculation is the new top production rule of the grammar. It expresses the loop in calculate and allows us to do several calculations in a run of the calculator program. It relies on the statement production to handle expressions and declarations. Okay, so we can handle a statement like this. So here's this new function called statement, which we're going to switch on what kind it is and say, well, if it's a let statement, then it's a declaration, and we're going to call declaration. Otherwise, we're going to put back so we're going to get a token. If it's a let token, then we're going to call declaration. If it's not the let token, we're going to put it back and call expression. So we can use the statement instead of expression in calculate. All right, where are we going to, shall we copy this into our, maybe we should copy this. I'm going to put that on the clipboard and paste it into the comments at the beginning, huh? I think that would be a good idea. Okay, and there's all this talk from 6.3, which is no longer really relevant, right? So here's our grammar. And the way you remember the spelling of grammar is that just think of grandma. Yeah, never mind. So a calculation, yeah, right. So a calculation could be any one of those, and a statement could be a declaration or an expression, and a declaration has the string let followed by a variable name followed by an equal sign followed by an expression. All right, so that's the syntax for our declaration. Okay, so with that in mind, let's go get the code for the statement function. And where should we put that in the code? I'm thinking down towards main, maybe, right? We have expression here, and this calls expression, which we've already declared expression earlier. Where was the scrolling. Yeah, I guess if I go here and say expression. I get the okay. So here was declared, right? So we have to put calculate after, or statement, sorry, after expression, right? But we have primary, sort of the simplest expression. Term is the next simplest expression, and expression is a sum or difference of terms. And then we have the cleanup mess, which maybe we should put this between those two things, huh? Okay. So we don't have a let token yet, right? So let's see what, and we don't have a declaration function. Okay, so let's go get declaration and see what to do about the let token. So we can now use statement instead of expression and calculate, right? So I think the only difference here is going to be right there, right? So let's go to our code and see down here, instead of calculate, well, incalculate, I guess. Yeah. The output of result, sorry, yeah, we're going to call here statement instead of expression. All right, and the rest of it is exactly the same. So we now have to write declaration. What should it do? It should make sure that what comes after the token let is a name followed by an equal followed by an expression. That's what our grammar says. What should it do with the name? We should add a variable with that name string to and the value of the expression to our vector of variables called var table. Once that's done, we can retrieve the value using getValue and change it using setValue. However, before writing this, we have to decide what should happen if we change a variable twice. So if we do this, is that allowed? No. Once you've added it to the var table, you don't want to add it again. It'll be like, oh, you have two variables with the same name, which is possible in a vector of variables, right? You know, they could have two variable objects, both with the same name, maybe different values. Which one would you get then? That would be ambiguous, and that's not desirable ambiguity. So we choose to consider such a redefinition an error. Typically, it is simply a spelling mistake. Instead of what we wrote, we possibly meant, let v1 equal 7 and v2 equal 8. There are logically two parts of defining a variable with the name var and the value val. Check whether there's already a variable with that name in the var table. And then add var val to the variable table. What if it is already there? We have no use for uninitialized variables, right? We define the functions isDeclared and define name to represent those two logically separate operations. Okay, so we're going to have a function called isDeclared and a function called define name. And where should we put those? Well, let's see. I think up here before statement, right? Because statement is going to call declaration, which is going to have to call these other things, right? So I'm going to put in a little separator here and paste in isDeclared, which takes a string and says for every variable in the var table, if that's there, then return true. If we get to the end of our var table and not find it, then we return false. That's fairly straightforward. And so if is declared returns false, then we can declare define name, which is going to add to our var table. And this is the constructor for our variable. Do we have a constructor for our variable? I think it's a global variable, right? And yeah, there it is, right? Oh, you can't see that, huh? So when I click on this little tab up here, I get a menu that says global. Well, it's under the global scope. You can kind of see that. It's small. And then the variables with global scope are token, token stream, and there's the token stream definition here, and then variable. So if I click on variable, it jumps to that. And I see that I don't have a constructor for my variable. Can we get by without one? I mean, you are allowed, you're given a default constructor if you don't define one, right? And what does the default constructor do? Well, the obvious thing for a default constructor to do is to set the member variables with whatever is in the parameter list. Will that work? Well, I'll have to think about that, huh? So I'm going to go, yeah, so if I go back to statement, is that where we are? Oh, yeah, well, somewhere around here, right? It doesn't like it here, right? It's saying no instance of constructor matches this argument list, right? So it's not obvious, which one is first, which one is second. These are the two member variables of our class, but I think we better go ahead and make a constructor. Can we just put it right in here? Let's just put it right in here. So I'm going to say variable, which is going to take a string n and double v, and in the initialization list I'm going to say name is going to take n, and value is going to take v, and we'll have an empty body. Okay, so now if I go back to oh, that's funny. Okay. Back to here. So now this constructor is not complaining. Okay. We still haven't defined declaration. Let's see what he says about that. Adding a new variable is easy. That's what pushback does, right? This constructor makes the appropriate variable, and pushback then adds that variable to the var table. Given that, and assuming that we can handle let and name tokens, which we don't know how to do yet, declaration is straightforward to write. All right. Let's examine it. I'm going to put it on the clipboard here, jump over to the code, and this is calling declaration, so we should put it perhaps here just before statement. All right. And this is assuming that we have seen a let token, and we're going to handle the expression name equals expression, and declare a variable called name with the initial value expression. So if we get so we're assuming that the only way to get to declaration is to encounter the let token. So we're assuming that's already happened when declaration is called, right? That's the only way you would declare new variables, if you see let, right? And so here we get the next token, and that had better be a name token. Oh, well, we don't have that either, right? So we're going to have to make a name token. If it's not a name token, we're going to throw an error, right? Because if you see the key token let, then that's got to be followed by a name token. So then we're going to assign var name. So what's var name? Oh, we declare a new variable of type string called varName, and we're going to give it the string which is name's name. That's a little confusing, huh? So we get a name token, and the first field of a name token is the name. All right, um, which is going to be a string, right? And we assign that to the var name string. We get another token, uh, and that had better be the equal token, right? Which is a single character. And if we don't get that, we throw an error, right? So there's a lot of ways of going wrong here, right? It's got to be just so. And then the equal sign should be followed by an expression. So we get that expression, assign its output to a variable of type double called d, and then we're going to construct our name, right? Our variable, and that's define name which is right here, right? Okay, so it's all fitting together nicely. Let's see what he says about these tokens. Now that we have returned the value stored in the new variable, that's now what we returned was the value stored in the new variable. That's useful when initializing expression is non-trivial. Yeah, so here let v equal this, fairly complicated expression. D divided by delta t, it looks like, where d is going to be one variable and t1 and t2 are two other variables. And when you encounter a name token like d or t2 or t1, you're going to see, well, is that in my var table? If not, throw an error. If it is, then return its value, right? So this is going to involve looking in the var table for three different variables and substituting their values in that expression. So printing the value of a declared variable simplifies the code in calculate because every statement returns a value. General rules tend to keep code simple, whereas special cases tend to lead to complications. Yeah. When at first you begin to dissemble, what a spider's web you weave, and so on. All right, so the mechanism for keeping track of variables is what is often called a symbol table and could be radically simplified by using the standard library map. Right, this is exactly what map is about. As a map has a key and a value. The key is unique and is used to look up the value in the map. In Python, it's called a dictionary. It's a very similar kind of thing, but it's a little confusing because I think Python also has something called map. I'm conjecturing here. I dimly remember some confusion along those lines. I don't think C++ has anything called dictionary. Let's try to verify that. Okay, so I will go here, and there's Scott. So C++ dictionary, I don't think it's a built-in type, is it? The dictionary class, modern C++. Okay. Oh, map. Right. So map is the C++ standard library's implementation of the concept of a dictionary. It contains key value pairs where the keys are all unique and the key values are used to find the associated values, much like the real word dictionary. The map is, just like most of the standard library, implemented using templates, and the types of the keys are values, and the values are given when you create the map. Okay, so they give some examples and so on, right? All right. So we have yet to define our tokens that we're going to need, right? So introducing names. 782. This is all very good, but unfortunately it doesn't quite work. By now that shouldn't come as a surprise. Our first cut never, well, hardly ever, works. And here, we haven't even finished the program. It doesn't yet compile because we have no equal token, but that's easily handled using a case to the token, adding a case to the token stream get. But how do we represent let and name as tokens? Obviously, we need to modify get to recognize these tokens. But how? Well, here's one way. So let's put these in the in that section at the beginning. Which is up here somewhere. Yeah, where we had these global constants. So I have a global constant of type char called name, and we're going to use the lowercase a character to represent a name token. Why not lowercase n? I don't know. L for the let token. Okay, that's again just a character, so it doesn't have to be a string. But we do need a key, the declaration keyword. So if we get the keyword let, then we're going to construct a let token with that we're going to create a declaration token. Well, that may work. That's what he's suggesting. Let's try to follow that thread in the text. Okay, and then token stream now is going to be modified so that if we have something in the buffer, we just return that. That's what we had before, right? We're going to switch on the character, and if it's an alphabetic character, then we're going to put it back. Why? Well, much like because we want to get the whole string, right? So if we get an alphabetic token, is alpha, right? Says is it an ASCII character in the range, you know, of alphabetical characters, right? Then we're going to put it back just like we did with the variable, you know, then get the whole string, right? Using cin's, you know, space separated feature, right? And so if S is the declare key, which as we saw over here, that's the string let. So if we get a string which is the word let, then we're going to return the let token. We're going to construct a let token and return that. Okay, so I guess this is going to be under the default section of get. What about yeah, so this as before, so he doesn't repeat. There's a whole bunch of code here, right? Which we're just not going to, so we're going to say in the default section we're going to have this now, right? Okay, let's go to the code and look for token stream. I guess we have to go over here for token stream, right? The token stream definition. Oh, it didn't go there. Oh, I think right after that is where get is defined. Well, ignore, here it is, right? So yeah, we get a character, and then we're going to switch on that character, and in the default section here we're going to have this whole well, let's just write it out. Okay, so it's going to say if is alpha of our character, then we're going to put it back, right? So, and this is not the buffers put back. Well, it's the console buffers put back, right? And so we're going to call cn's putback function, and also known as unget. Well, unget is slightly different. Then we're going to declare a variable type string s, and we're going to cn s, and if s is the declare key, did we? I think we defined that. Okay, so that is defined up above. Then we're going to return the token constructed from let. That's a thing, right? Yeah. We put that up in our global constants. And if it's not the declare key, that means that it must be a variable name, and we're going to look it up. Well, what are we going to do? We're going to construct a token, which is a name, a variable name. Notice he's using the more standard curly brace construction syntax here, but we don't know how to construct a name token, do we? I don't think so. All right, so he's going to have to deal with that. And the rest of this is the same, right? So we got a little bit of a problem here, so let's read up on that. Strustrip. So note the first call of isAlpha character. This call answers the question, is CH a letter? Yeah. For more character classification, see 11.6. The logic for recognizing names is the same as that for recognizing numbers. Find a first character of the right kind, here a letter, and put it back, and then read the whole thing. Right. Unfortunately, this doesn't compile. We have no token that can hold a string, so the compiler rejects this constructor. To handle that, we must modify the definition of token to hold either a string, a double, or a double, and handle three forms of initializers, such as just a kind, right, which is, plus, minus, times, and so on, a kind of number, so a number token, or a kind and a name, right? To handle that we handle that by introducing three initialization functions known as constructors, because they construct objects, right? So we now will add the okay, so here's the operator constructor. Here is the name. Oh, sorry, the number constructor, and here is the variable constructor. So this is the new one, right? So I'm going to go to the token constructor. All right. Which, let's see, can I get there here? Okay. And just to add another line here, right? Name. So name is taking a string. So this is the initialization list, right? And we're saying the first thing is going to say what kind of token it is, And so if the parameter list for our token constructor has the second parameter a string, that means that this should be the character A for a name type, and this, why doesn't it like the name here? Name is not a non-static data member or base class of. Oh, right, because I haven't. Yeah, so I need a new member variable, right? So this is going to be string name. Okay, so our token class now has 3 member variables. Kind, which is going to be what? Either an operator, the character 8 for a number token, which is also, we renamed that simply number, or the character lowercase a for a name token. So this is a variable name token. Okay, so it seems to like that well enough. All right. You suppose we're getting close to something that's going to work? Okay, so we choose capital L, the character capital L, as the representation of the let token and the string let as our keyword. Obviously, it would be trivial to change that keyword to double, var, octothorpe. That's this is an octothorpe, right? Or whatever, by changing the string declare key that we compare S2. Yeah, all right, so it's sort of arbitrary, but it's a global constant, and we're done with it. Okay, so now we try the program again. If you type this, you'll see that it works. So yeah, good luck with that. Let's give it a try. I don't see, scrolling through, I don't see any IntelliSense tingling. Yeah, no, I don't see anywhere where it's a problem. So I'm going to try to compile this. It's thinking about it. Okay, I've got it compiling. Here's our output window. I'm going to type in let x equal 3.4. Oh. Name expected in declaration. And we see that twice. I think that's just because that's the way the error function works. Name expected. But notice we recovered from that. This doesn't work. Oh, he says that this should work. Okay, so why are we getting this message here? I suppose we could go back to our program and search for that. Okay, right there, huh? So if we don't, so we're calling the get function from the token stream class, and assigning that to t. If it's not, so how do we get to call declaration? Who called declaration? Statement. Who called statement? Calculate called statement, right? And who called calculate? Well, that's the only function called in main, right? So we go calculate calls statement. Statement gets a token, and if it's the let token, which it should be, right, then we call declaration. And we did get here, right? So we called declaration, and we got the next token. Right? Because we've seen let, right? And the next token was, we said let x equals, right? So the next token was the character x, or the string x, if you like, right? So get didn't work properly. So we go back up to get, which is here, and say, why didn't we construct a, so what is get doing? So it's getting the string x, right? Is there something in the buffer? No, I don't think so. So we get the character x, and we switch. Is it one of these guys? No. So we go down to the default. Is x an alpha? In which case we put it back. So let's see if we get here. All right, I'm just curious to see if we even got there, right? If we did, we should, return a name token, right? So here's the output. I'm going to say let x equal 3.2, whatever, right? Ah, so we did get there. Okay. So I guess we don't need to see that anymore. So we put back our x. We get a whole string, and the string is just going to be x, right? And if that string is equal to declare key, return the let token. It's not, right? It's x. Otherwise, we're going to return the token constructed this way. All right, and so what happens next? Well, maybe I should check to do, let's say, I just want to check, okay? Token t equals token name, I guess we could use the curly braces, name s, right? And then I'm going to see out got t.name, right? And then I'm going to say, yeah, you could just leave the rest of it the same, right? So, and maybe let's put an end line here. All right, so let's test that. Let x equal 3.4. So it didn't get there. It didn't got that. So why not? Right? If s equals, then return. Oh, maybe it didn't get past here, huh? See out s equals s. When in doubt, see out. I am in doubt. I'm in a world of doubt. So here's the output window. I'm going to say let x equal 34.3, whatever. And s equals let. What is it doing with let? It's supposed to be x. We already got let. Okay, so that's what's going wrong, right? Oh. Well, yeah, I mean, this is how we get the let token, right? So we get the let token, we construct the let, we return the let token, and if we have the let token, so statement calls declaration if so here we're assuming that we've got the let token, and this actually happens, right? So then we get the next token. the one after the let token. And that should be our X token, right? So what happens when get has, okay, so if we have X as a character, we're going to put it back and yeah, so the first time we get let, well, let's run this again. So I'm going to say let X equal 3, and so then it says name expected in declaration. So we're getting to that point where we've gotten the let token, sure enough. And let's see, we don't need this, you don't need that. Okay, so we've gotten the let. We're here, we get the X. Do we get the X? Maybe this is a good time to take a break. Think about that. Any insight as to why or how to recover from here? I mean, Strustrup says these should work, right? Yeah. All right. Well, it's a good time to take a break. I know it's a cliffhanger. We're stuck. All right. So take 10, and we'll figure out what to do about it. And, well, anybody figure out? Okay, so what's going wrong? The declaration is called because we got the let token, right? We only get to here if we got the let token. If so, we call declaration. All right. If we call declaration, then we get the next token, which should be the X variable, right? Oh, yeah, let X equal, right? And so if it's it's not getting the name token. Oh, I think we didn't provide for that, did we? No. Okay, so where was that? Where were we supposed to do that? Right, so if we get a lowercase a, then we're just going to, yeah, okay, so we need to do that right in here somewhere, right? It's going to be one of the operator tokens. Oh, no. Yeah. So it was in get, right? So what did he say about get? Did he have a way of handling the I think we just have to add lowercase a or name, right? So so here's where we, this is how we construct a number. So we need somewhere where it says name val, right? Or name comma name. That's a little weird, huh? Oh yeah, it's right here, right? Name. Okay, and we never get to here, right? All right, so what are we doing? Is alpha. So the character we got is X, right? We put it back. We get X as a string. If and so then this never happens, right? We never see X spit back, right? So how come we don't get here? Okay, so we have, it's confusing because the name is used twice. Once as a constant character A, and again as the string, the variable name S, right? Okay, but that's right here, right? But when we get x as a string, at this stage it should say s equals x, right? Because we got string. It's not one of these other tokens, right? Okay, so declaration calls get to get a token. And it does that after it gets the let token. And that's happening successfully, right? So then we switch on what kind of token it is. And if it's none of those, right? And it is none of these, right? It's not a number token. It's not an operator token. It's a name token. So we end up in the default section, right? And where we say, is it an alphabetic token? Yes, it is. It's X, right? If so, then put it back, get the whole string. So it could be like X1 or X2, and that would work, right? And so we get that string, and we spit it out. But that's not happening. So, in fact, instead, what's happening is we're not getting a name token. So token stream is getting the next token. It should be a name token because it's going to get the alpha character X. Let X, right? And so we got the X. And so we switch on, is it a name token? And we're getting no, right? Why is this not happening? Okay, so statement calls declaration. Well, statement gets the let token. If it's a let token, then we call declaration. Statement gets a token. If it's the let token, then we call declaration. Declaration gets a token. And that had better be a name token. And it's not a name token, right? We get this error message. So why does it not get a name token? So ts.get is going to call this get function up here, right? So is there anything in the buffer? I don't think so. Cout. There's something, let's say a token. Okay. And I'm going to assume that there's not. So we get the character, which is X, which is, oh, look at that! Look at that little puppy right there. Oh no, it's an X. Crap. Let's get rid of that. Jeez, sometimes I gotta tell you. All right, so let's try it again. Here's the output window. I'm going to say let X. I should have chosen some other variable, right? 2.3. Okay. There's something in the buffer, and S equals X, and it's got X. But now it says bad token. Oh. But we got X. And S equals X. Okay. So let's, but why are we getting bad token? What does he say about this here? This works. x plus y times 2. But this, oh, right, and the difference being here that we have spaces, right? So we got to deal with that. But we're also getting bad tokens. Why are we getting bad tokens? Right, our output window is saying bad token, bad token. But after we got x, so let's clean up that stuff and figure out what would happen next, right? So, all right. So let's just delete that annoying thing. Okay, so it's saying bad token. Okay, so we're saying, yeah, we got the thing. I guess we can get rid of that. And this. Let's see if just getting rid of that maybe cleans things up a little bit. So output. Oh, that's a different output. So let x, I'll say x1 equal 3.4. Bad. I can only one bad token this time. There's a token in the buffer. Oh, now it says bad token, bad token. There's 2 bad tokens. Can I get rid of the token in the buffer message? Where was that? That was in get, I guess. Right here, yeah. Okay, so so let x equal all right. So we were able to get the so we passed this test here, right? And so we will then have a name because we constructed a name token. And that, don't confuse that with the first parameter, right? Which is the character, constant character called name, which is the lowercase a. This is a string, which is the second field of the name token. And that's going to be assigned to the string var name. Then we're going to get the next token, which better be an equal sign. That seems to happen correctly. Then we get an expression. And so is this, I'm going to go back to the strustrup and see, is this, did I do this correctly? This was the declaration, right? So get a token. If it's a name, if it's not a name token, throw an error. If it is a name token, get its name. Get the next token, make sure that's an equal sign. And that's happening correctly. Get the next thing, which is an expression. And then use that expression to construct a variable name, and then return that value. Why is it saying bad token? Who says bad token? Isn't that get? Yeah, get says bad token, right? Anybody else say bad token? Primary? Where's primary? It's down here, huh? Oh, I think I have it minimized, huh? Does no, primary says this expected, right? Primary expected. Okay, that's primary. Well, maybe why are we getting bad? Oh, I think it's because I don't. Oh. So default says if is alpha, then do all that stuff, return a token, and then say bad token. But only if you don't return a token. Well, let me do this. Oh, I'm in the code. I'm looking at what happens here. Oh, what happens here? So I'm going to create a variable type token t and set it equal to name s, and then say cout token name s constructed. T dot name. Oh, T dot kind. See, this is what's confusing, right? That should be an A, I guess. And this is going to be T dot name, right? Right. I know that's, see, that's what's in a name. Okay, so let's see. Is it actually going to do that is my question. So if I say, here's the output window. If I say, let x13 or x12 equal 4.3. Yeah. Okay. But then bad token, bad token. Why bad token? What if I say x12 now? Primary expected. And why is there the semicolon? Huh. All right, well, we got some questions. But down here you can see this. Why is this a problem? Let's just move on and we'll maybe figure out what the heck is going on at some point. What's the difference between those two examples? Let's have a look at, see what happens. The problem is, okay, so you get the string and it's space-separated stuff, right? So we got an alpha character x, and we put it back, and then we got this whole string. This is our variable name, right? This whole string. This is supposed to be an expression, right? Here, supposedly this works, although it doesn't for us. Why is that? I don't know. Maybe we should get the source code from the text and see if that doesn't improve things for us. So the problem is we were sloppy with our definition of name. We even forgot to define the name production in our grammar. Oh. What characters can be part of a name? Letters? Certainly. Digits? Certainly, as long as they are not the starting character. Underscores? Eh? The plus character? Well, Let's look at the code again. After an initial letter, we read into the string using the cin extraction operator and accepts every character and sees a white space. So this could be a whole variable name here, right? Even when the trailing semicolon is part of the name, right? So that's unintended and unacceptable. What must we do instead? First, we must specify precisely what a name is meant to be, and then we must modify our get to do that. So a name could be any alphabetic character followed by anything except, well, you know, in C++, you can't have an operator as part of a name. So we want to disallow that. But any integer or alphabetic character, um, and or an underscore. Um, well, he's saying this is not a variable name. Yeah, well, underscore can be problematic in a variable name. It's used for special purposes sometimes. Certain kinds of names start with an underscore. Um, and yeah, you can't have an asterisk. That would be a pointer. And you can't have a space. Except for leaving out the underscore. That's C++'s rule. Okay, so we change our default. So we get an alpha character and then add um, the character to that, and then while we get alphabetic and digital characters, keep adding those in, and the first character that's not one of those we put back, right? And we don't add it to our ongoing string. So let's take this as our new code. I think the rest of this is the same, actually. Okay, I'm going to go back to the code and say this part okay. So if we get an alphabetic character, then we're going to create an empty string, add that character to our string, concatenate operator. Then while we get a character that is both, well, so we're anding an or here. If either one of these is true, then we're good, right? But you know, this or statement has got to be true in order for us to add that new character to our variable name string. And the first one that is not alphabetic or digital, we put back. And if we get the let string, then we construct a let token. Otherwise, well, let's see how this works, if this works better now. I don't think it's going to work better, right? Because we didn't change, well, let x123y. I mean, that's a variable name, right? Equals 42. Bad token, bad token. And then if we say x123y, it should, so it's telling us again that we've constructed this token. And then it says primary expected, primary expected. So why is that happening? And why, when we get a variable name, does it not look it up and write that to our file? So I'll tell you what, let's go to, I think actually at the end of chapter 7, there is some kind of working code for this. Let's take a look there. So I'm going to say add existing item, and oh, I don't have the chapter 7 stuff in here. And you can't see what I'm looking at here. I'm looking at the directory with the variable names in it. I am going to have to go get that. Okay, so here we go. I'm going searching for that. I found this instead. Okay. Okay. So I'm going to go here. I think I just want to go here. And programming code, chapter 7. I'm going to separate by types and get the CPP stuff. I guess I'll get all of that. And then I want to go here and paste it in. And then if I go back to our code, I see now I have 7.83. I think that's probably pretty good. Should we take a gander at 7.83? Oh, sorry. That's the wrong thing. Try that again. Existing item. 7.8. I got the text file. I think I want this one. Okay, so now I have these two things open. I could look at them side by side if I could remember how to do that. Or we just go back and forth. Notice he's got now a nice revision history dating back to 2004. 2007 is the last entry there. Yeah, what about C++14? Isn't that part of? Yeah. Well, he was probably hatching that at that time. All right, so we, oh, yeah, I think we have all of these. We have this constructor here. I don't know, why is this underscored here? 4 overloads? Could be because I have, oh, it says value is uninitialized. Let's see. Okay, so here's our constructor for the token stream. Here's our putback function. No big surprises there. So the token stream has a constructor, it has a get function, has a putback, and ignore, right? The token has 3 member variables and 3 constructors. There are global constants. The get function, read characters from CN and compose a token. All right. Oh, you see, he's got all these on different lines. I kind of don't like that. I'm real miserly. Is that the word for it? With my lines. It's just because I don't like to scroll through a lot of stuff. I guess I could, you know, do that if I don't want to scroll through it, huh? Okay. And here's this, yeah, this is just what we were doing, right? Okay. That looks very much like what we have. Here's our ignore function, and that is just doing what we usually do. Here's our variable class. The var table is a global variable. Get value, right? And so who calls get value and set value? I think maybe we weren't doing that. Is declared. Searches through the whole thing and says, did you find it? Right? If so, then return true. Define name. We talked about that. So add a variable to the var table. Primary. I don't know why this is indented here. Okay. Switching on the kind, so primary could be an expression in parentheses. It could be a floating point literal. If we have a negative sign, then we just negate the call, another call to primary, right? Okay, that's primary. I think we can be fairly happy with that. Here's term. Now, again, these case statements are oddly indented. And yeah, see, he's doing the modulus operator this other way. I guess, do you want to bring in our way instead? I don't kind of like, I really think that ours has a little bit more meaning. So we can go to, oh, that's standard library facilities. Go to, where is it, term? Where we handle that case. I'm going to copy that and put it here. And just to make sure, you know, it's yeah, we both have a break, we both have a get. Yeah, let's just get rid of that one then. All right, there's term. Expression is a sum or difference of terms. Yeah. Now that is just as we expected, right? Declaration. Now so here's where things might get a little bit different than what we've got. So let's maybe compare that declaration with our declaration. So we get a token. We say if it's not a name token, then we are in the wrong place. Otherwise, we get the equal sign. What? Oh. So we have a name token, and yeah. So is that what we're doing here? Yeah. Then we get the next token. Then it better be an equal token. Then we get the expression, and we construct. Oh, define name. Or is that what we were doing here? Yeah, define name. And what does define name do? Where is that? I'm searching through this. You can't see what I'm doing here, right? There's a drop-down menu here with declaration. It doesn't have define name. Oh yeah, define name. There it is. Okay, so define name calls is declared. It looks to see is this variable in our variable table. If it is, then we throw an error, right? Because we're declaring it twice. Otherwise, we construct it and push it onto our var table and return its value. Is that what define name is doing? Do we have a define name here? I don't see it. It's declared. Oh, we got this big long get function. Can we go here to find it? Define name? Oh, there it is. Okay. Oh, I see. Yeah, same thing, right? And again, you know, why not just concatenate them like that, right? Although, yeah. So yeah. and then return, right? So there's declaration. Statement. Okay, so this statement, is that the same as our statement? So our statement, we said get a token, switch on whether it's the let token or not, right? If it's not the let token, then we put it back and call expression. If it is the let token, that means we got a declaration. I think that's the same. Okay. And then cleanup mess is just calling ignore with print as its argument. Calculate, put out the prompt. Get a token. Yep. While that's the print token, keep getting tokens. Essentially eating multiple semicolons if need be. If it's the quit token, then we're out of there. Return 0. Oh, this just says return. Same thing, huh? Well, this is calculate is returning nothing, whereas here calculate is returning a double. Oh, that is a little bit different, isn't it? Why were we returning a double? So let's make this a void function. And then when we say return, we'll just not return anything. And really there's only one statement in there, so we can say it like that. That's a little bit cleaner. So yeah, if it's the quit token, then return. Otherwise, put it back and call statement. Statement returns a double, right? So that's what handles the returning a value. Okay, I'm going to get rid of the other one and see if this one works. So this is 7.8.3, which is very much like we just made a couple of small changes, but maybe that will do the trick. I'm going to say exclude from project. All right, save whatever changes we had there. I'm going to try this one. Does this compile and run? All right, and here's the output window. All right, so I'm going to say focus. Let x equal 2.3. Oh, okay. It must have been that return thing was a little bit wrong, huh? So now if I say x, does it say 2.3? Yes, it does. What if I say let y equal 3.4? Okay, and then if I say x plus y without spaces, 5.7. I can verify that in my head. Looks pretty good, huh? What if I say let x equal 5? So you can't do that. It's going to tell me twice that I declared it twice. Well, that's how error has a redundancy built into the cake. All right. How about sign of x? Undefined variable sign. Yeah, so I could say let sign equal 4, and then say sign times x. That would be wrong, though. I mean, that's 4 times, what's x? Yeah, 2.3. What if I say x equals 3.4? 2.3, and then primary expected. So I can't assign a new number to my existing variable x. So, and it also is giving me the primary expected error. So that Yeah, that will say declared twice, right? If you try to redefine an existing variable, it throws an error, which it recovers from, which is nice. But we should have some way of reassigning a value to our variable, right? It shouldn't be hardwired forever. I think that takes us back to Strustrup, who's going to address that very issue. So predefined names. Geez, we may actually get done with Chapter 7. Now that we have names, we can easily predefine a few common ones. For example, if we imagine that our calculator will be used for scientific calculations, we'll want pi and e. Where in the code would we define those? In main before call of calculate, or calculate before the loop, or in calculate before the loop. We'll put them in main. Okay. So, and you just hardwire these predefined names. I can do that, or I can copy and paste. So here's oh, they're already there. Sorry, this is the and we don't need this keep window open thing. Oh, okay, so it might be here where, yeah, I mean our main was just calling calculate, right? I mean, essentially, we had just that calculate, right? Which the rest of it being the same, and we don't need this keep window open thing. All right. So, need a reset command. Yeah. Okay. So, but now, yeah, that's a good point. So F5, if I go to the output window, I wanted to test that I've got pi times e, and yeah, it'll give me a value for that, which is easy as pie. All right. Are we there yet? Comes from the back seat. How much farther? Well, no. We've made so many changes, we need to test everything again, clean up the code, and review the comments. Also, we could do more definitions. For example, we forgot to provide an assignment operator. If we have an assignment, we might want to distinguish between variables and constants. Oh yeah, exercise 3. Initially, we backed off from having named variables in our calculator. Looking back over the code that implements them, we find we may have two possible reactions. Implementing variables wasn't all that bad. It took only about 3 dozen lines of code. Or we could say implementing variables was a major extension. It touched just about every function and added a completely new concept to the calculator. It increased the size of the calculator by 45%. And we haven't even implemented assignment. All right. In the context of the first program, significant complexity, the second reaction is the correct one. More generally, it's the right reaction to any suggestion that adds something like half of your existing code, additional lines, right, to a program in terms of both size and complexity. When that has to be done, is more like writing a new program based on a previous one than anything else, and should be treated that way. In particular, you can build a program in stages, as we did with the calculator, and test it at each stage. You are far better off doing so than trying to do the whole thing at once. All right, so the drill. Starting from get the calculator to, oh, we got a buggy. We got another buggy. So where's the buggy? I don't think it's in the, is it? Let's see if it's in the existing source code. So if I say add existing item, calculator 08, no. So we'll have to go to the browser and say, oh, great browser, find for us this thing. And we're having trouble finding that site. Don't be an idiot. Oh, I see. It's put a www there. Oh, it just adds the www. I guess because it's got a field. All right, so just search for that. Okay, there it is. And we'll just copy that onto the clipboard. I guess we'll remove the existing thing. Add a new thing, which is going to be calculator 08. I don't know why 8, but whatever. Oh, and buggy. All right. Helpful comments removed. We have inserted 3 bugs that the compiler will catch and 3 that it won't. All right, so we got our token structure. It's got the 3. We're missing a constructor, aren't we? All right, you can see there are 3 member variables, and we're just missing the constructor. So I don't think the compiler would catch. Well, maybe it would. Okay, so the first one is going to be, I guess this, oh, the second one is going to be a string name, right? And we're going to say kind character, and is that correct? Oh, well, let's put an N here because we do have. So this is going to be for the variable token, whose constant character is. Are we missing the constants? Looks like we are, huh? Oh, here they are. Let's put those at the top, right? So, yeah, a little confusing that we have a constant character called name, which is going to be a lowercase a, and that's what's going to go in that position. Where the second one, okay, so that's going to be lowercase a kind, and a string n for the name. All right. So there's our constructor. Let's hope that that's all right. And then the token stream. Shouldn't that have, that has a constructor. It has a get function. It has, now this is unget, right? So he's changed putback to unget, just to keep us on our toes. But that's okay. It's just the name of the function. And in fact, there is also an unget associated with the buffer, the console buffer. All right. And I don't know. I think that's all of that, isn't it? Then we have get, and there's probably some stupid get in get. Oh. Yeah, notice he's using yeah, he's using the instead of putback with a parameter of type character. This is unget without any parameters, and it just whatever was in the buffer gets put back. What there's a staging area for the buffer, and so it goes from the staging area back to the buffer to be gotten again. And can I do it like a Control K, Control D? Because it seems like, okay, so So we're switching on the character. We're looking at all these cases. And I really don't like it like that, so I'm just gonna, there. So in that case, we're gonna return in all of those cases. Is that covering all the waterfronts there? All the various operators? Looks like it. Maybe missing something. Oh. So that should be indented, shouldn't it? This is the, sort of the body of... I don't know why that's... So in the case where you're getting a number token, you're going to construct it that way, right? All right. And then the default case, we're going to check to see, is that an alphabetic character? If so, create an empty string, concatenate that character with our string, while we can get a character that is either alphabetic or digital. Ah, look at that. Dirty, sneaky. See, I don't think the compiler would catch that, right? That should be a concatenate here. And it was missing the plus sign, right? All right. So if you, as soon as you get some character that's not alphabetic or digital, put it back. If you got the string let, then construct a let token. If you got a quit, then what? No, I don't think that's right. I think basically we can just say, if it's not the let token, then construct a name. I don't think this isn't where we handle quit, right? Can we just get rid of that line? And this is the ignore. Who's been counting? I haven't been counting how many errors and what kind of errors. Plus we're getting short on time, huh? Let's see. So we have our user-defined type variable, which has two member variables, name and value, and a constructor. Sure. We have a vector variables, which is now called names. It used to be, oh, that's terrible. Yet another use of the string name. Now with an S at the end to distinguish it from its two other instances, where one is a string and one is a constant character. Yeah, what's in a name? So you're sort of playing with variable collision here, but not actually encountering it. Yeah, those asteroids are passing in the night. So get value, does that, yeah, I don't think there's any, is there a problem with that? It returns a double, which is the value of the variable it finds in the table, and if it doesn't find it, it throws an error. All right, set value. Looks through the table. If it finds the string, then it sets the value, right? So this is what we want to call when we redefine a variable, right? A variable's value. Oh, there's a lot here, isn't there? And plenty of room for potential problems. I think this is okay. And a primary. He's not handling the plus here, right? Should we handle that? Do we care? If you get a plus sign, we just want to return primary, right? Um, if it's a number token, we return the value. If it's a name token, we get the value and return. Get value returns a double, right? And this returns a primary returns a double, so that's good. Otherwise, primary expected term. We have times and divided by says, look, if you're dividing by 0, then you should throw an error. Otherwise, yeah, we're reaching the end of our time here. Let's say that that's okay. And what expression calls term, handles plus and minus, some are difference of terms. Again, it's using unget instead of putback. That's fine. Oh yeah, unget is our token streams function, right? Yeah. And declaration, oh gosh. Yeah. If it's declared, we throw an error. If let is not followed by this, we already know we have a let, right? If we're in declaration, then we got a let. So then we want to get a name token and look to see is that in the variable, in which case variable table. All right. Well, we don't have time for a lot of further investigation here. Let's just see what happens if I try to run this now. Does it have a compiler error? No, there's no compiler error. How does it work? Well, let x equal 3.4. No problem. If I say x, it says 3.4. Hey, how did that happen? Yeah, who's paying attention? Oh, yeah. Oh, if I say x equal, no, this was the problem, right? Yeah, so that's still a problem. That's exercise 3, which I will invite you to examine over the weekend and finish up the drill. But looks like we kind of got most of it. So shall we say x times x? Is that 11.56? I think that's right. Let y equal 0.01, and so y minus x. Oh yeah, of course we don't have y, right? That's y234 minus x. That's okay. All right. So let's, we just got a couple of minutes here, so I'm going to go to the browser and look to see how did we do on our proposed agenda. Well, we didn't, that's a tough problem. We have to come back to that. There's another challenge. Oh, we didn't talk about life. Well, let me say this about life, which, where is it? Oh, here. This guy, Richard K. Guy, he also died. I missed that one. And this is a paper that he published last year at the age of 103. So I think he was 104 when he died. I've met this guy. I sort of drew my breath, and let me point this out about Guy, which is can I? Maybe I can use this other here. This is the authors here are Elwyn Berlekamp, John Conway, and Richard Guy. So we lost both Conway and Guy in the last month or so. Wow. This is one in a series of volumes. I think there are three of them. Winning Ways for Your Mathematical Plays. Highly recommended. Um, and Here's a paper which you can find. I think this is freely available. I'll tell you what, I'll put it in the comments. Um, Guy is the one who solved the problem of infinite life, right? So life can grow infinitely by creating this, what do they call them, streamers? Um, but yeah, I guess we'll have to close it out there. It's now time, huh? So let me go back to here, and I'll just add a comment here. Any questions or comments before we? Yeah, I know I'm behind on a couple of things, like yeah, reading stuff. I've been sort of busily creating a midterm for the 7B group, and that's kind of a nightmare. Just writing distractors is not my cup of tea, and it just bring out the evil in me. Oh, what is it that they think might be right that's actually wrong? um, Sorry. All right. Yeah, so we'll have to take up the calculator where we left it off and work out the first few exercises in chapter 7, and then we'd want to get to chapter 10. We may have to skip through parts of 8 and 9 to get to 10, where, we just want to be able to read and write from files, which I think is an important concept. All right, well, seeing no further questions, I will bid you a pleasant afternoon, and see you next time.